So, thanks everyone for coming along to the talk. My name is Christopher Batey. I work on the Akka team at Lightbend. I've been doing this for about 6 months, which is about the right amount of time to give this talk, as what I'm going to do is talk about all the features and stuff we've been doing for the last 6 months and kind of look forward to the stuff that's in progress now but won't be ready for the foreseeable future. I'm guessing, given we're at Scala Days and you've chosen to come to the Akka talk, you know what Akka is. We're going to be touching on most of it today. So we've obviously got the core actor model. I'm going to be talking about Akka typed and the changes to the API and the internals for that. That has a knock-on effect on most of the rest of Akka. So we'll be looking at clustering, 2 parts of clustering. We're going to look at multi-DC, and we're going to look at some of the typed APIs. We'll have a look at persistence. So Akka type probably has the most effect on persistence, because you don't just have the one type, you don't just have the messages you're sending to actors, you have the events you save, and you have the state that you build up and potentially snapshot. HTTP is quite interesting, so I'm going to talk about something which is very, very new. We just released a preview release of it last week, I believe, for running gRPC on top of Akka HTTP. So I think that's everything. The reason we're going to be talking about typed, the prototype has been around for quite some time, but over the last, say, 3 months, what we've tried to do is get it to the point where we'd call it production ready, and we'd be happy for people to start, building their regular actor stuff with typed rather than untyped. The multi-DC stuff, that is probably the oldest feature I'm going to talk about, so that's ready to use. It's in a released version of Akka. gRPC, as I said, is very new, so I'll show you how that works, how you can program using Akka streams for gRPC and use Akka HTTP as the underlying HTTP 2 engine for that. One thing I missed out in the previous slide was I'll be talking about Artery. Artery is the newer version of remoting, and it's currently been UDP based, but we've just released a TCP based version, which also has TLS, which is what a lot of people have been asking for. And I'll briefly talk about stream refs, which is taking Akka streams and being able to materialize them on a different computer inside a different actor system, so you can get the benefits of flow control and reactive streams, but between servers rather than just on a single server. So, first topic, Akka typed. So, who here has played with the Akka typed APIs over the last year or two? A few? Anyone running it in production? No, last time, I've done one talk previously on Akka typed, and his company had said, oh, we're using it in production. Oh, we changed most of it, unfortunately. So Akka typed prototype has been around for quite some time, and it was made up of 2 things. It was the underlying runtime had changed, so there was a new implementation of the actor system, and then there's a completely different API, which is unsurprisingly more typed than the previous one. So that we can make it production ready and recommend that you use it rather than the regular untyped actor API, what we've actually done is remove the new runtime, which means that you only run Akka typed on your regular actor system. There is a new thin wrapper, so you interact with it in a different way, and I'll show you that today. But the goal is the next few releases of Akka to say, yep, this is ready to go. We'll probably leave, the API may change on it, but the actual quality, etc., should be there for you to be confident to run it in production. So I'm going to start off with an untyped actor, show you it in a couple of different ways of doing it, and show how that relates to the new Akka typed APIs. And I'm going to do it by doing something quite ridiculous, which is to build a distributed lock with Akka. So when you're doing untyped Akka, you can obviously send any message to it. And a good practice would be to still represent the incoming messages as a sealed hierarchy, and maybe the same for the response messages. So maybe a very simplistic distributed lock or lock would be to say I want to be able to lock it, and I want to be able to unlock it. And if I ask to lock it, I'll get something back saying, yep, you've been granted, or I'm sorry, some other actor's got this lock. And one way of achieving that inside untyped Akka would be to use some good old mutable state, which some people might not like. And what we're essentially doing here is representing a kind of state machine, but where the state is inferred from the mutable variables. So some people, even in this very simplistic example, it can become confusing. You kind of try to reason about it, and you think, oh, if the owner, if it's taken, I can kind of accept these messages. If it's not taken, maybe I can accept these messages, and I think this is pretty hard to reason about. So my background coming from an Akka user rather than someone working on the Akka team, I would probably prefer to explicitly represent the states as different partial functions. So one for unlocked and one for locked, and then I can very explicitly see in the top here that if I'm in the unlocked state, then yep, I accept the lock message. If I'm in the unlocked state, I accept the lock message. Or if I'm in the lock state, then I can accept both, and I tell people, no, you can't have this. And then we use become to change behavior after receiving a message. But you notice one of the sections here we didn't do a become, which is fine, right? You can remain the same behavior. So what would this look like if we were to do this in Akka typed? Well, unsurprisingly, we end up with a type parameter. We're not going to be extending any classes or using traits here. This implementation here made quite a bit of use of the sender, right? The implicit kind of the function that you get this magic sender so you can send back to. And if we were to look at our protocol, even though we were saying we're going to lock the message, we weren't saying who we were. So in Akka typed, you have to be far more explicit about this because the sender, for instance, what type would it be? There's nothing forcing you in Akka typed that even though you know what type you receive, there's no way to know what the type of the actor is that sent you the message. So there's a bit more explicitness when dealing with request response protocols. The other thing that's gone away, and I'm going to show the alternative, is that you can't use actor selection. So this was a way of taking an actor path and then getting an actor reference and then sending whatever messages you like to it. But again, there's no real way to do that if you're going to be typed about message interactions if you're without some unsaved cast. So if we remind ourselves fundamentally what an actor is, when we receive a message, we can do one of three things. We can send messages to other actors that we already have the references for. We could send messages to actors where the actor reference is inside the message, which is quite common. We can spawn some children and create some kind of party, or we can change our behavior. And we'd implicitly change behavior before with become or by mutating some variable. So what would this look like in Akka typed? Well, the protocol has to change slightly because if we're going to communicate with some actor and we want a response from it, what we're going to have to do is send in a reference so they can respond to me. So both lock and unlock end up with an actor reference inside so the lock actor can say, yep, you've got the lock or you don't have the lock. To show some of the more complex features of Akka typed, I've extended the response protocol. So we have granted, and we're just going to do that. We're just going to say it's granted. The taken, that still takes an actor reference because we had that before. And I've added a couple of messages in to say that it's been released or the unlock has failed for some reason when unlocking. So let's see how that looks like in Akka typed. So for each of those things which you would normally create a separate partial function for if you were doing untyped actor, but you were following the kind of paradigm, the guideline of using become and switching between states if you weren't using FSM, then you create something called a behavior. And there's a factory for creating these behaviors, but they're essentially functions which go from the actor's protocol, so the message that the actor reference is typed to the next behavior. So before when we were kind of doing that with become, but in this example we have to explicitly do this because we are actually providing a function here which needs to return a new behavior that needs to be of the same type. So if we were to look at the case of being locked and someone else were to try and get the lock, we'd send back saying that I'm sorry it's taken, but we'd end up with the same behavior. So there's a factory method for that. So that's the top case. However, if we were to get the unlock, then we would need to become unlocked and we return a new behavior, and that can be a value or that can be a function, or it can be a method where you're storing state inside the stack. So the top one is a function, it's not a partial function, so you'll get the appropriate compiler warning if you decide to miss out some of that at a type hierarchy. Whereas the unlocked one, we want to ignore some messages. So there's also factory methods that will accept partial functions. You're essentially saying you don't handle the other messages. These are quite simplistic, and we'll see some more complex ones soon, but there are also a set of factories where you get hold of the actor context as well. So here, these are completely contained by the messages coming in and the messages you want to send back. But often, if you want to do things like spawn children or do other things like set timers, then you're going to need an actor context. Now, The next thing I want to see, imagine that we start off this actor, which is going to be a distributed lock, and if we have a reference to that actor, then we can just pass it in while creating other ones. But I'm going to assume we're running in some type of clustered environment where you want to look up a particular lock. And previously you might use actor selection for that, and you might identify and you might see if it exists. In Akka types, we want to be able to do this in a type-safe way. So locally within a single JVM, the API is the same, or whether you're running inside an Akka cluster, there's a service discovery for typed actors. It's called the receptionist. And that's something which is on the actor system. So if you have an actor context, you can always get hold of the receptionist. And you can register. So you can say, I'm of type X with name Y. And other areas of your code which need to look this up, where it can't be done by just passing in a reference, they can either find a particular typed actor or they can subscribe and get updates when new instances of that actor are created and registered, or whether one of them dies and it's removed. So the receptionist itself is a typed actor. So you interact with it with messages. A simplified version of the protocol would look like this. You can either find, which gets you a one-shot, please tell me if there's any existing right now, or you can subscribe. And what you get back is a listing of actor references, which then you can communicate with. So let's see how we'd use the receptionist. So in this example, we're not just creating a behavior, we're actually creating it's using a factory to create behavior, and it's called setup. And the difference here is you first get hold of an actor context. So the type of this, the context on the right there is an actor context. And we can use it to spawn. So I'm spawning one of my unlocked actors with name lock A. And then I can register it with the receptionist. And the receptionist is only going to accept messages of its command, which in this case is register. Once I've done my setup, then what I need to do is return the next behavior, the behavior that's going to process the first message for this actor. In this example, it's in a function called needs_lock instance. Before we jump into that, I want to talk about ask, because we're going to use ask in the next one. So one of the problems with Akka typed is when you interact with other actors and you're expecting a response back. And the example here is the receptionist. Now, it's very unlikely that your type is going to be the type of message which the receptionist is going to send back to you, if that makes sense. So there's a set of helpers and functions which are going to enable it easier to interact with typed actors. And one of them is the ask pattern when you're an actor asking a question of another actor. And what you do here is you pass in the actor reference. So in this example, it's the receptionist. You pass in then a function to create the message that you want to send to that actor. And then finally, you pass in a function which deals with the response. So the idea here is that you want to turn the protocol of the other actor, in this case the receptionist, back into your protocol, so you can actually receive the message. In this case, we basically say, if it's successful, in this case it will deal with things like timeouts, and we have a listing, then we're going to send the lock actor is available to ourselves, and that's of our protocol. That one will type check. Otherwise, we send lock not available. What do we do in this case? So, well, the first thing we need to do is ask for a actor reference. We need to find a lock. And in this example, it's the same code as in the previous slide. We basically ask the receptionist in a setup method, can you please find me the lock? And then what we do is, because that response that's come back from the receptionist has been mapped into our protocol, then we deal with it. So we can either say the lock actor is available. In that case, we ask it for the lock. Otherwise, if the lock was not available, maybe it's crashed, maybe no one's registered it, then we can do behaviors.stopped. And at that point, the actor will shut down. One of the other differences with Akka typed is your actual actor system is an actor reference. So you actually have a top-level behavior. So I could type this to actor system or of a actor reference, and I can start interacting with it. And it's very common for your top level to be a setup where you initially kick off your initial actors, etc. So that's kind of like the whirlwind tour of what the Akka typed API looks like. You'll say goodbye to sender. You'll start to deal with a bit more complexity when you're interacting, because you can't just sneakily accept another message type, which could be from some receptionist, say. The other thing I want to have a quick run through is if how this has changed persistence. Because if you've not used persistence before in Akka, it is a way to do event sourcing. So you take in messages, so you're dealing with a regular actor, but this time we normally refer to those messages as commands. You do some stuff, you validate it, and you decide what events you want to persist based on it. And once you end up with millions and millions of events, you might end up snapshotting, so you don't need to replay and build up your state back each time. And it's very explicit in Akka typed for that. So this is a very simplistic, silly version, but essentially we have three types. We have commands, events, and states. They can be whatever type you like. The commands and events were typically some kind of hierarchy of types. And then what we have is another factory for creating persistent behaviors. So the persistent behavior factory, that takes in a persistence ID, it takes in initial states, and then it takes in two functions. The first function is the equivalent to your receive method on a regular typed actor, except this time you do get the state as well as the message and the context. And then as part of that command handler, what you do is you decide which events that you want to persist, and then that's passed into your event handler. So what does a command handler look like? Well, it's a function which takes a command and a state and a context, and you have to produce something called an effect. Now, an effect can be to stop. You could ignore the command, maybe it's not valid, maybe in your current state it isn't valid, or you can persist one, or you can persist many events. And that's all you need to provide for that, and that's just a function. The other is the event handler. So every time you produce an event from a command handler, it comes in, and then essentially you need to produce a new state based on that event. So it's a lot more explicit than the old version, and it allows us as a library to do more things for you. Previously, we didn't really know that if you had a state, and so if you wanted to snapshot, that's something you would decide, and you would call a method called snapshot, and that could be any type you like, as long as you had a serializer for it. Now it's very easy for us to say, okay, because we know about the state, and we know, say, there's a serializer for it, you could easily just tell us to snapshot it every 100 events. We can also make things like event adapters, which we're working on right now. They could be more type safe. And tagging becomes easier. It's very common to tag events in these styles of systems, so you can query them different ways on the read side. Previously, that would have been done inside your persistent actor by wrapping it in a tagged case class or with an event adapter. Whereas another thing on the builder for a persistent behavior is just to say, here's a function from event to set of tags, and then we'll persist the tags for you. So that's about it. That's the type section. A few things which I haven't covered, but there's a talk later in the day by Heiko, which I imagine will cover more of this stuff. The first I think is most important is coexistence. So how would you migrate over to using typed rather than untyped? So you can create typed, you can adapt between the two systems. You can create typed actors from an untyped system and vice versa, so that they work really well together. Other lifecycle events, which you typically override a method for in the actor trait, that's another handler. So signals like whether you get things like terminated and you want to be notified of starting and stopping and things. So you can still do that. We have some new test kits, which very much more explicitly distinguish between async testing and synchronous testing. Because behaviors really just are functions, then a lot of the time you can just test them synchronously more easily. It gets a bit tricky if you start kicking off async events and things, but it's still, for a lot of times it works. And there's a few, any time which you were dealing with an actor reference in streams, there's an equivalent module now for type streams, but that's very minimal. Right, so the next thing is multi-DC. So simply put, multi-DC, which was the oldest feature, so this has been around for 6 months or so, is running Akka cluster across data centers. Now, there is nothing stopping you from running an Akka cluster across two data centers, if that's what you want to do. But all the things which happen internally with inside cluster, so gossiping and membership decisions, etc., they all wouldn't take into account that the latency between certain nodes would be higher. And the way that Akka cluster works, where things like membership decision and things are not made if there are network partitions, etc., it's obviously more likely to have a network partition or another data center down when you're dealing with geographically distinct locations. So I'll just go through the kind of decisions that were made. And I think most of the decisions that have been made, I think from my point of view, are to expect the other data center to be down or expect there to be some kind of partition. Because if you're running across multiple data centers, my assumption is you're doing it because either for fault tolerance, so you actually want to be able to handle a catastrophic outage of a particular data center or someone tripping on a wire, or data locality with customers. So things like membership management, that's all done local within a data center. So you have a leader per data center, and it will make the decisions. So if you have a network split in between two of your data centers, data center A on one side can still add members, etc., and make decisions on that. Singletons and sharding. So I'm going to sneak in some more type stuff when I show you the API for this, because every time I show you examples, I'll use the typed API rather than the untyped one. So a cluster singleton, unsurprisingly, is something which runs once. And if you have two data centers, the choice would be to run one across all of them, or whether you would want to run one per data center. And we decided that it would be a singleton per data center. By default. So if you were to run the same code with the same configuration, you'd end up with one per data center. However, I'll show you the APIs and how you would go about just running it in one data center if that you want. And the same is said for sharding. So if you're using cluster sharding and you send messages to a particular entity ID, and you do it in two data centers, you'd end up with two instances. But you can still use things like distributed data. You can still use things like regular Akka messaging to communicate between your two sets of nodes, rather than having to break out like a separate protocol like gRPC or HTTP. So what you do is you tell each node which data center it's in, and then everything you knew about Akka cluster before will happen within a local data center, but then there'll be slightly less frequent gossiping between the two data centers, so each of the sides know about what's going on the other side. And you can register for events like unreachable data center, etc., and if you need to do something based on that. So let's see how we would use something like sharding or singletons. The APIs are quite similar for them. So at the moment, deciding which data center you're in is just config. There's been some ideas about automatically picking this up in environments like AWS and Google Cloud and things like databases like Cassandra do, but it's just config at the moment. Here's the typed API for cluster singletons, and the one for sharding is quite similar. So we're spawning a typed actor. The only thing that's really changed between this and the old one is that the message you use to shut down these actors, it has to be of the protocol of that actor. It can't be something like a poison pill, because that wouldn't type check. And yet we can send messages to that. If in data center B you wanted to have another singleton managing something, or another complete set of cluster sharding, then you would just do the same thing. But alternatively, you can say, actually, I want to talk to a singleton, but I want to talk to the one data center A because I want to make some global decision that wouldn't be available if I were to have some kind of network split. So you depict consistency over availability there. An interesting thing to note here, we saw what looks like quite a complicated ask API before, where you passed in a function to map that message, the response message, back into the protocol of your actor. That was for when you're having one actor talk to another. If you're talking to an actor from outside of the actor ecosystem, so just from a regular Scala code, then it looks a lot more like a regular ask. You just send it a message. But there's no map to there, right? And what ask actually takes is a function which produces the request message of the actor, and it passes you an actor reference for the response. So this get value is actually a case class which takes in one parameter, which is an actor reference of the appropriate type. Okay, so that's multi-DC. The other thing that's changed, and this was quite recent and is definitely still in preview mode, but it's ready for you to try out on your network infrastructure. It's not Artery, just Artery. It's specifically Artery TCP. So some time ago, a new version of remoting was released, which is based on Aeron, which is the libraries by Martin Thompson, Richard Warburton, and Nitsan Wakart. But a lot of people can't migrate to that because, one, it doesn't have transport security, and two, it's based on TCP. And depending on what network infrastructure or what your IT department will allow you to do, maybe this isn't right for you. So Artery, unsurprisingly, is built on top of Akka streams internally. So what we've basically done is separate out the UDP Aeron specific things and done an equivalent implementation for TCP using Akka streams TCP. And it's really nice then because you get things like TLS, so you can start to have transport level security again. If you haven't looked at Artery yet, 'cause you saw UDP and ran away, then there's some other cool things about it. It separates out system messages and control messages. Aeron, when using UDP, actually has the concept of multiplex stream, so it will do that for us. In this, for TCP, at the moment, it's separate TCP connections. So you have a control TCP connection, you have a large message stream if you enable that, and then you've got your regular ones, just to stop big, large messages clogging up the pipe between your various actor systems. So, next thing we worked on. So streamrefs, quite a simple feature, and if you've come across the problem, you'll find it very useful. Otherwise, you might think, why do I need that? So my assumption is a lot of people here have used Akka streams or some reactive streams compliant a library for processing things, and that they know what back pressure is, etc. And all of that is normally built for a single JVM. Right, so it's inside your application. How do you deal with the flow of messages when things are asynchronous and you're not getting that natural thing by blocking lots of operating system threads? What streamrefs is, it takes this concept and puts it over the network. So there's nothing stopping you from doing this yourself. So if you are Akka streams based or something else and you want to communicate with another reactive streams or Akka streams based thing, then you could hook it down. You could go down to TCP. You could make sure then that your TCP flow control maps up nicely with your flow control within your application. But you're suddenly dealing with serialization issues. You're going to have to start dealing with getting down to a byte string rather than Akka just handling it for you via serialization extension. You'll start to have to worry about connection pooling depending on how you do this communication. And the other side needs to be listening. So you need to worry about port allocation, etc., which becomes even more complex. So what streamrefs is a way to take this, where you've got an active system here, an active system there, and you realize that it's not just an odd message. You actually want to send a significant flow of messages from one to the other, and you want to do it in a flow-controlled way. Because if you were to just do this with regular actors, you'd end up with all the problems that Akka Streams is trying to solve. You'd probably end up with lots of mail, and you'd end up blowing up the other system, especially if you didn't hook it up correctly with Akka Streams TCP and deal with the TCP flow control. So the quick primer on how it works regularly inside a one JVM is anytime there's an async boundary, anytime we're sending messages from one part of the stream to the other, then the only way that happens is the demand flows back. So the consumer of messages picks the rate. And basically it does this but over the network. So the API is very simple. You can take any existing source and you can run it with a streamref and it will materialize and you'll end up with a future and that may change, of source ref. A source ref is just a source. It will be implicitly converted for you. However, if you want to explicitly call .source, and then somehow you can jump over, get that to another node. How you do that is not really the concern of streamref. That could be a regular actor message. It could be over anything you like. And once you've got hold of that, and this could be a sink or a source, then you can materialize it the same way that you can run it, the same way you would normally do it. And the advantage of doing this is under the hood. What's going to happen there is we're going to have message ordering, we're going to have redelivery, we're going to have demand propagating back from one actor system to the other, and you won't see this will just be happening under the covers. The demand propagation, the kind of protocols which you might have built by actor messaging, that will be resent and retried under the covers. And if you create lots and lots and lots of these, but no one ever materializes them, then they'll eventually time out, so you don't end up with some type of resource leak. Right, so that's streamrefs. If you've ended up with that problem, then this is a good thing. So the final section, probably the biggest new thing, is Akka gRPC. Is anyone using gRPC in the audience? A few? Is any using a different RPC frame, like Thrift, anything? No? So normally, as a team that likes messaging, we wouldn't normally suggest using an RPC framework, but it's become a de facto standard. It's become very popular. For those of you who don't know, it's based on HTTP 2. It's language agnostic, so you take a interface, you have compilers which turn it into a language of choice, be it C#, F#, Scala, Java, and then it allows you to communicate between two services. It's based on protobuf, if you've used that for serialization before. One of the differences between this and other attempts at this, like Corba, is streaming is a first-class citizen. So if you've not seen this before, this is what an interface definition language looks like inside gRPC. You've got 4 types of request-response patterns or patterns. The first is the simple one. So this is going to be our distributed hello. So we first end up with one where we just send a small request, and we get a small response back. That's the top one. I'm assuming these messages, hello request and hello reply, are defined somewhere, and you can put whatever you like in there. Think of them as a case class. That's what they get mapped to. But then you also have the use case where you're sending lots of data. So it keeps talking is prefixed with its input parameter is prefixed with a stream, but its response is just one message, and it keeps replying is the opposite. It returns a stream. So the idea is there is you would kick off something and then you get lots and lots of responses back. And then obviously you can go full shebang and you can decide, hey, I'm going to stream both ways. I'm going to send you lots of stuff and I'm going to receive lots of stuff. Now this is something which I would imagine would work very well with Akka Streams, right? An API based on this. The API you dealt with if you use the default kind of Java one is something called a stream observer. So anytime you end up with stream inside your API, you end up either having to interact with this or implement this to deal with the messages. It's not the most composable thing. So we see what this looks like with this. So the Akka gRPC support, it's an SBT plugin which will do the code generation for you. It also supports Maven or Gradle if that's your thing. And it'll generate you stuff for the client, so a client-side stub, and it will generate the machinery which allows you to implement it with Akka Streams and then plug it into an existing Akka HTTP infrastructure. So say hello actually knows nothing about Akka or Akka Streams. That just uses the regular standard library feature, and you would implement that however you chose. The streaming ones, I think, is where it's a really good fit. So the assumption is if you're doing this, then you're not going to have a 4 GB hello request. It's going to be small, and it doesn't matter if you materialize and pull this into memory. But if you're going to send lots of things, the idea is to use one of these streams. So a stream inside this becomes a source. So what you basically do is if you want to implement this on the server side, you'd have to hook up your sink and consume from that source to deal with it. And that would happen in your regular flow controlled way that you would expect from Akka Streams. And responses are always asynchronous, so you somehow turn that into a feature however you like. On the other side, so we want to actually send back lots of things, that also becomes a source, but you return a source. And the idea then is in the Akka gRPC infrastructure, what it would do then is it would sync it up and attach it to gRPC and send it over the network. And if you just love streaming, you can stream both ways if you want. And you could base the source that's coming in, the source out, or they could be completely independent. So there's two cool things I think about this. One is the fact that you don't have to deal with the on-stream observer thingy-mabobby. You get to deal with Akka Streams, which I hope is a nice API. The other is the fact that, and I don't think there's anything else that can do this, is you can co-locate this with your existing Akka HTTP infrastructure. So the stuff that's generated, what you can do is you get one of these greeter service thingies. Mine was called greeter service, so it's now called a greeter service handler. You pass in your implementation, and what you get back is something which is a HTTP request to a feature of HTTP response or an Akka HTTP route, which means that you can combine it and just pass it in. And at the moment, it's only with HTTP 2, but this will change, and you'll be able to upgrade existing HTTP 1 connections, or you can do that with TLS, but not without TLS right now. Which means that if you have clients and some of them want to do gRPC because the internet told them to, and some of them want to do HTTP because that's the thing, then you can actually serve all of this stuff over the same port, and you could have all your Akka HTTP routes. You could combine it with this, and you could serve it from the same thing, which I think is pretty cool. On the client side, it's unsurprising. You end up with the same interface. So as a client, you interact with the same interface that I showed you that you'd be implementing if you're on the server side. So if we end up here, you end up with a client, you just tell it where to go, and it will connect in. And unsurprisingly, because I've already showed you the API, if you call one of the unary requests, which is the one without streaming, you get back a feature. If you end up with one where you have to pass a stream in, you're passing the source in. Or the other way around, you end up with a source back, and then it's your responsibility to hook that up to some sink and consume it. Otherwise, you'd have the same problem where you didn't consume the response entity, say with Akka HTTP client. So to summarize on gRPC, this is very new. So I think we released the 0.1 release this coming week or last week. So don't put it in production just yet. It only works with bind and handle async with Akka HTTP. The server side is fully Akka HTTP. It doesn't have any dependencies, but the client at the moment is based on the Netty version. But the idea is that this will eventually be based on the Akka HTTP client once it supports HTTP 2. So if you're used to using things like Cinnamon, if you're a Lightburn customer and you're monitoring these things and you're monitoring your Akka HTTP infrastructure, you'll get the same for the things that you do with gRPC. So that's everything we've got time for, or everything that we've actually managed to do in the last 6 months. So I've looked at typed. I hope that people really now go and play with typed because we're at the point now where we wouldn't want to make any fundamental changes to the API. We've made a few over the last few months. We don't want to break it anymore. I think gRPC is quite exciting. So on that note, I just want to thank you for listening. I think we've got about 5 or 10 minutes for questions. So thanks very much. Any questions which I may or may not be able to answer? No? Yeah, what's the... cluster thingy? So yeah, lightbend offers split brain resolver. I think there's nothing you really can or cannot do once it's split. So the idea that you don't want to do inconsistent things during a split brain, and that could be accidentally end up with 2 lots of cluster sharding or end up with 2 singletons. But because all decisions are local to a data center, actually once the two TDDCs are split, it actually makes the leaders can still do exactly the same thing. So there's like, that split brain is handled by the fact that we don't make, Akka cluster never makes cross DC decisions for you. You'd have to build your own logic based on something for that. Any more questions? Yeah. I think they'll be around for a long. So the question was, what will be the future of untyped actors? So it's subjective. I think they'll be around for a long time. I don't think they're going away. I guess it'll be based on the success of Akka typed on how long they remain. I think we're at the point now where I guess we'd want to start implementing a lot of our internal stuff with Akka typed rather than untyped actors. But you definitely, my experience from using it is you pay a cost because if you want to do something quick and hacky, which I would never do, then you suddenly can't just accept a new message into your actor. You have to explicitly think about the protocol interaction, which can seem quite boilerplate initially, but I think you thank yourself later down the line when you go back to that code. Any more questions? I think I saw one. Yeah. So the question was, is there anything new in persistent query? Well, persistent query was already fully typed because you were dealing with streams rather than any actors. So as far as I'm aware, there's nothing new. You still interact. Persistent query doesn't really know whether things were persisted either with Akka persistence typed or regular Akka persistence.